All right, today we are going to talk about the importance of significant figures and identify the correct number of significant figures. So first, I want you to take a look at this set of rulers. Right? There are these gray lines. Right? Which of these rulers do you think is best? Now you might look at these and say, well, what do you mean best? Well, which of these rulers allows you to get the best or the most exact measurement of each of these lines? So what you might notice here is, all right, this is somewhere between 9 and 10. Maybe you say, hey, it's 9.5, but maybe it's 9.6, or maybe it's 9.4. Can't really tell exactly. But this one, if you look, all right, hey, this is like pretty close to 8.5 on the dot. Maybe I could even guess, hey, that's 8.49. Take a look at this one. See how this has all those extra little tick marks? All right, I can look at this and say, hey, this is 11.9 exactly. All right, now there's no units here, but if we pretended it was centimeters, we could put centimeters on the end of this. So in science, we have different tools to measure different things. In this case, these are all rulers, but some of them allow us to be more precise than others. This is a mass balance. If you notice here, this only has one decimal place. So, if I put this pair of scissors on it, it might tell me that these scissors are 12.2 grams. But if you look at this thing here, this is called an analytical balance. All right, see it's got these windows on the side. If you notice, this goes to 1, 2, 3, 4 decimal places. All right, so the type of tools you're using are actually going to tell you how many significant figures you have. All right, we'll talk about what that really means, but it's basically talking about how many numbers can you know in your measurement and not just guess at. So we're going to be talking about these things called significant figures, right? And two key vocab terms would be accuracy, how close a measured value is to the actual value, and then the other word is precision, how close the measured values are to each other. So if you have a measurement tool or you are doing measurements in lab and you are both accurate and precise, you are right on target. All of them in the middle. All right. But let's say you're measuring and you're not so accurate, but you're pretty precise. All right. Accuracy means you're not really hitting that bullseye, all right, if you're not accurate. But precise meaning you're pretty close to each other. So maybe there was something wrong with the mass balance, or the ruler was like cut off and you were just missed it wrong, but they were all close. Now, if you're accurate but not precise, right, your answers might be kind of around the bullseye. And the reason why a lot of times in lab you might do multiple trials is to account for that. If you took an average of this, you would probably end up pretty close to the bullseye. And then if you're neither accurate nor precise, your, attempts are going to be everywhere. So use the idea of this like target or arrow, but you could think of this in terms of measuring volume or measuring mass or length, etc. So precision and accuracy are important to understand how good the data is that you're collecting. Right? So if you think back to those rulers, you would be most likely to be most accurate and most precise with that ruler C, the one that has all of the individual marks. All right, so this would be an example I give in school, but think about how you could measure the distance you walk from, my classroom, which is usually A231, to the office. All right, like maybe I could say, hey, one of my steps is about 2.5 feet, and I count how many steps I take, multiply that, and get it. Or maybe I have a tape measure. All right, think about which of those would be accurate and precise and how good of a measurement you could actually get. Here's an example using volume, all right? So when we're getting measurements, there's always some type of uncertainty, all right? So if I look just here, all right, without the zoom in, I can tell that this is between 40 and 45. If I look here, 1, 2, 3, it's somewhere near 43, all right? Now, as we zoom in, all right, you can look and see that. When you have a volume, or a mass or a length, you try to take a guess as to whatever that next digit is, all right? You determine significant figures so that you include one uncertain digit. So kind of made a little mess with that line here. All right, so if I look at this, all right, remember you always read from the bottom of the meniscus. If I look at that really closely, I see that it's 43, all right? Pretty confident that that's going to round to 43 no matter what, all right? Now, I could say this is more than just 43. It's right on the dot, so I'm going to say this is 43.1. But my lab partner might look at it and say, hey, it's 43.1. Right? I say 43.0, they say 43.1. Who's right? I mean, really, we both are, because the idea is that this last digit is the uncertain one. Now, if they said it was 43.7, well, we might need to reevaluate that, and they're probably looking at the top of the meniscus instead of the bottom. All right, so significant figures basically tells us how good of a measurement we have. All right, so what there's going to be is we have some rules for significant figures. If you've got a number and it's not 0, it counts. It's something that's measurable. So in this number, 45,900, the 4, 5, and 9 are all significant. So what we would say here is that this number has 3 sig figs. All right, we usually just abbreviate it SF, but this has 3 because of those non-zero numbers. If you have a captive 0, which is a 0 in between any significant figure, all right, this would be an example of a captive 0. Right? We've got 405,900. All right, we would say this has 1, 2, 3, 4 sig figs because those are all able to be measured. All right, now zeros start to get a little tricky, but here's the important part, is if a decimal point is present, then the 0 to the right of a significant figure is what is going to count. So a decimal point tells you that you're able to be accurate. All right, so this would have 1, 2, 3, 4, 5. 5 sig figs here. So all of the underlined ones count because this decimal point is here. All right, we weren't just guessing about those two. We know it. It's 45,900 exactly. Not 45,901, not 45,899. It's exactly the way it is. All right. This, all right, only has 2 sig figs. All right. Leading zeros, numbers in front, are not significant. They're just placeholders. You could also rewrite this in scientific notation, right, which we'll talk about later. And the whole purpose of that is that in scientific notation, the coefficients, or whatever number goes in front, those are the only ones that count. So that would have 2. Okay? This one here, 45.9, would have 3 significant figures. And then this one, 4.05900, has 6 sig figs. Okay? So once again, a significant figure is just saying how many numbers or how many digits are present that you are actually able to count and measure. Right? If you have an exact number that is an infinite number of significant figures, if I say there's one person in this room right now, it's not, there's 0.99 of a person and not 1.05. That's one that is infinite sig figs. All right. Any other zeros that you have that don't follow the rules we had previously are not significant. So if you've got 0.0 405. All right. The 4 and the 5 are good. This 0 is in between, but those two don't count. So we would say that there are 3 sig figs here. All right. So here's kind of a little recap. Why do we use them? All right. There's always uncertainty in measuring, so we report the values to one uncertain digit. All right. I could tell you that the width of a soccer field is about 70 meters. All right, so I'm estimating that's only one significant figure here. All right, if I said, right, maybe I did the steps to count. If I said that it was 70.0 meters, all right, that has a decimal point next to it, then it would be 2. Right? Because this first 70, maybe it was only 68, maybe it was 72. Right, I'm estimating. This one could give you a little more accurate. All right, maybe I got a tape measure out and I measured it to 68.6 meters. Now I've got 3 sig figs. That's more accurate, more precise. Now, if I were able to tell you that it's 68.59231.342 meters, that's probably unlikely. Right? This number here would be to the nearest millimeter. Right? That 2 there. So getting smaller than a millimeter, highly unlikely. All right. So sig figs tell you how good your measurement can be. All right. So here are 2 examples with the answers, and there will be a Google form below, hopefully, to have you test this out. All right. So 1, 2, 3, 4, all 4. They're non-zero, so they're significant. All right. This one would have 2. All right, so take a second and think about the next ones. How many would each of them have? All right, this one has an 8 and a 9, so those are significant. All right, but there's not a decimal point there. So because there's no decimal point, it only has 2. This decimal point here makes it significant. You could think of this one as more of an estimate and this one as an exact number. Using that same idea for the last one, we should have 4 here because the zeros in between are captive, but this one doesn't count, and then 6 because there is a decimal point there. All right, so that is your little bit of information about significant figures. Let your teacher know what questions you have, and enjoy your practice problems.